We have Professor Shanker, and he is getting connected from Mary Medical College and Vanderbilt University, Nashville, Tennessee.
Hello, can you all hear me?
Yes, we can hear you. Are you able to hear me?
Yes. So let me share my screen. Can you all see my screen?
Yes, we can see that, and now you are all set to go.
All right. So thank you to the organizers, Professor Anuchan Bharti, Professor Anish Srivastava, and the chair of the session, Professor Rana Pratap Singh, and everyone else. It's always good to speak at the alma mater. I planned to come, but somehow did not come. So I know that I'm in the mid of your dinner, and so I will try to be brief and succinct and not bore you enough with too many details. So I'm going to tell you some facts and some thoughts that underlie the disease that we have in human population. So I will start with this journey of human evolution and migration. And if you see on the left here, about 200,000 years ago, human species as we are today, Homo sapiens, that arose somewhere around 300 to 200,000 years ago in South and Southeast Africa. And these studies are published by various groups, including K. Thangaraj at CCMB in India, and there are multiple validations of these studies as published in Science and other journals, and they show that first migration happened about 170,000 years ago, with a stop in India that happened about 70,000 years ago, and then the migration bifurcated downward to south towards Australia, where the establishment of human population happened about 50,000 years ago, and the upward migration went into Siberias in 25,000 years ago and came to Americas up to about 15,000 years ago. And this was the first recorded migration of humans. And the two other colors here, the yellow color, those are Homo erectus, and the lighter yellow, that is Homo neanderthalensis. And so there have been an intermixing of some of these human species or early hominids also, as was noted earlier this week by the award of this Nobel Prize to Swedish geneticist Svante Pääbo, who showed that until up to 30,000 years ago, Homo sapiens and Neanderthals and also Denisovans, they were very closely living together and interbreeding also. And so our genetic makeup is a mixture of some earlier hominids and the current migratory patterns that I will come in the next slide. But to make the point that we all have some Denisova-derived version of hypoxia genes, for example, EPAS1, which provides a survival advantage for those individuals who live at high altitude, like Tibetans. Likewise, people living in Melanesians have a high frequency of SCAT2 gene, which is important for innate immune response. And there are many examples like these. And so we all share about 1 to 2% Neanderthal genome and 1.6% of Denisovan genome. And just to make this point even stronger, what we are today is an admixture of genes from various migratory migration that we have had in the past, as well as intermixing with earlier ancestral hominids. And so this last wave of human migration happened about 5,000 years ago, and from the Eurasian region, the people living around the Caucasus Mountains, they expanded both ways, towards Europe as well as towards South Asia. And so currently what we are is a mixture of all these different genomes. And this has a lot of significance on human health. But unfortunately, genomics is failing on diversity. Many populations are left behind from precision medicine. And I will explain this more in detail. So we all know that today genetic information is used for diagnosis, prognosis and treatment of various diseases. For example, we rely on genetic screenings for early diagnosis and interventions of diseases like cancer, as for example BRCA1 genes predisposed to breast cancer. We also use polygenic risk scores to predict diseases on a set of genes. This is used for cardiovascular disease, diabetes, etc. And we now use personalized medicine, as is the theme of this session, and we do personalized pharmacogenomics to identify genomic medicine drugs that can target specific gene profiles, as we use that frequently in various cancers. But the problem is, if you see on the right panel here, on the left here, on the right here on the bar, you see this is the distribution of global human population. The red are the Europeans, all the rest are non-Europeans, and the Asians are more than 40% on this globe. But the mapping of genome has happened only for more than 80% Europeans. All other populations, which are in the bottom here, are very less represented. And so there is a problem in the mapping of human genome, and this means that the people living in this South Asia or Southeast Asia, they are more than 40%, and the treatment for these people rely upon Europeans or Americans. Let me explain this further. This means that the precision of precision medicine is extrapolated from information of European ancestry. If you see the bars here, this is the European population, and all other populations are less than 0.1% represented in the clinically relevant observations, because majority rely upon this population due to the deep sequencing of this European ancestry population. That means that gene variants for clinically actionable treatments, they disproportionately rely upon the people of European ancestry, and they lack validation in diverse populations, including Asians. This also means that the polygenic risk scores that we use for disease prediction is not accurate, as is now clear from this data set from the UK Biobank cohort, which is one of the largest studies as of today, which sequenced 500,000 people in the UK. And from that study we can clearly see that Africans has 25% disease prediction compared to Europeans, which have 100%. Asians have about 50 to 60% disease prediction. If you use the polygenic risk scores that are validated for Europeans, and this means that using that polygenic risk score would rather exacerbate health disparities in other populations. We also know that genetic variants and ancestry influence pharmacokinetics of drug metabolism and addiction. It is known that inherited variations in 20 genes are clinically actionable, and they affect about 80 prescribed drugs as of today. And we know, as an example, in Asians and Pacific Islanders, they lack CYP2C19 gene, and that is required for the metabolism of Plavix drug, which is a blood thinner used for cardiovascular patients. And if you see in the middle panel here, different genotype of individuals dictate the dose that population can have. For example, a population would have 8 milligram dose compared to some other population like African Americans, which would only can tolerate 3 milligram per dose of that drug. So that means that if we rely upon only one population to figure out the doses of the drugs, we can cause toxicity and lethality in other populations. This also applies in cancer, for example. On the basis of this genetic ancestry principal component analysis in different populations, if you see here, the lower left is European ancestry and the top here is East Asian and other populations like Native American and Africans. You would see that the lymphocyte profile in these populations vary. So on the left here, AC1 is the Asian population compared to other populations, and this predisposes these populations with low number of lymphocytes to different types of cancer like B-cell lymphoma as is shown in this example. So to achieve health equity, we need more inclusive genomics research that will lead to equitable and accurate genomic medicine opportunities. And so we saw this early this year that we completed the mapping of the human genome, but what we have not done is that we do not have in that genome diverse populations, and that creates a gap in the genomic diversity. As you can see on the right side here, most of the genome that is available to us as of today is 80% European. The Asians, overall they are 10%, but East Asians are 8% and all other Asians are less than 2%. Some populations are also less than 1% and some do not even exist there, like Native Americans. So there is a huge disparity in this human genome that exists today, and we need to fill this gap. Another problem is that community has a distrust on science, particularly genomics. And this is due to previous mistreatments and wrongful experimentations, due to lack of ethical guidelines that existed several decades ago. And this is one analysis based on 50,000 digital discussions in an example of African American population. And you can see that only 22% people have positive attitude towards genetic testing and genomics, whereas 49% have neutral attitude and 29% have negative attitude. So we have a huge window of opportunity if we can explain these people the value of genomics and science. We can create better healthcare opportunities for these individuals. So we established a new institute called the Diaspora Human Genomics Institute last year at Mehery, and the goal is to sequence diverse populations starting with African ancestry populations. Let me also clarify that we all on this earth trace back to African ancestry, and that's the reason why we named this institute the Diaspora Human Genomics, because we all are African diaspora as of today. So we have been working with the Region Round Genetic Center, which is sequencing different populations in the world and in different continents, including India, Israel, Pakistan and Bangladesh as of now. And so working with this consortium led by Region Round, we have been building an initiative that we call Together for Change Initiative. It's an initiative of multiple public and private partnerships involving African ancestry communities, historically black colleges and universities in the US, as well as African academic institutions and various industry and corporate partners in this initiative to advance science and empower diverse communities. The goal is to create a genomic data set for at least 500,000 African ancestry people and train diverse researchers at underrepresented and underserved institutions, expand genetic counseling and medical genetics workforce, and engage and educate communities towards genetics and genomic medicine. So I will end here with a thought that science can bring the change in community. It is important to lead with science, to take on big ideas, and to make it happen. As scientists, we have that responsibility in the community to deliver better healthcare and better education. I would like to thank you all for your attention and I'm open to any questions.
Thank you, Professor Shanker, for a very excellent talk and highlighting the gaps of the genomics and the health equity research. If there is any question to Professor Shanker? So, Professor Shanker, we don't have any question, and if there is anyone who is interested to know more about it, they will write to you in the email, and I think you can respond to them. So, thank you very much for your talk.
Thank you.
Thank you, Professor Shanker.
Any other question? Thanks, Anand.
Yes, hello.
Thanks, and it was wonderful talk. Yeah, it was a very wonderful talk. Very happy.
Thank you. Thank you, Alo.